Welcome to the lecture on metallurgical effect of heat flow on welding. So far we talked about how you can find the temperature distribution using certain equations because you have a point heat source which is moving along certain direction, and then certainly the temperature will be highest in that locality, and then you will have the temperature distribution or because of the temperature difference as you move farther away from that point. So accordingly you have the temperature distribution which we get, and from there basically we can get a lot of idea that how you can predict the properties of the material. So for that we need to know the cooling rate which is being experienced by the material, and that can be experimentally determined. So in this lecture we are going to have some discussion over that. But before that, as the title suggests, that metallurgical effect of heat flow. So in this lecture we are going to basically focus on how to find the what kind of cooling rate is existing when we try to have the temperature distribution. So once we get that, then there will be you can find the isotherms, and then accordingly you can have the cooling rate determination, and from there basically once you put it or once you use those TTT or CCT diagrams and try to have the analogy between these two, so then you can predict the microstructure, you can predict the properties of the material. So as we discussed that you have the different equations, and from those equations it will be possible to determine the temperature at any given point during the quasi-stationary state of welding. We will get the temperature at any given point. Now once we have such data, then we can find the thermal histories of these points, and then the isotherms for the different temperatures can be drawn. So you have to draw the different for different temperatures you have to draw the isotherms, and then from there the cooling rate also can be determined, which will help in predicting the microstructure of the heat affected zones, the properties of the zone. This is important because the heat which is flowing, so it's going to be dissipated all along in all the directions, and this heat basically will alter the mechanical properties, the kind of transformation which occurs in case of different materials, especially if you talk about the ferrous based materials, especially steels. So in those cases you will have there will be transformations which will be occurring, and that transformation can be predicted once you have the thermal history, once you have the cooling rate. So basically there is experimental determination of the cooling rate, and for that we normally the process is that we take a 6 mm thick plate. So we are taking suppose this a small thickness plate, so that is normally taken a 6 mm thick plate. So we are taking basically sufficient width and length so that you can establish the quasi-stationary state. So for that we say the width is taken as the 200 mm, and the length is taken as 300 mm. So that way you can, so the thickness will be very small as compared to width and length. So you can say that it's the quasi stationary state will be established once the the welding process has established through a length certain length like 50 mm. So that way, so your this length is 300 mm and this length is say 200 mm, and the thickness is certainly as is said to be that it is 6 mm. Now in this what we do is we are drilling the 3-4 mm deep holes at different points. So you will be drilling these holes, and what you do is from the center, so you have this line, and then you will have other points. So on these points what you will do is you will drill 3 to 4 mm deep holes with 1 mm dia. So you will be drilling 3 to 4 mm deep hole. So these holes are with 1 mm dia drill bit. So that way you can and then you will be embedding you will be fitting the the thermocouple into it. So you are drilling 3 to 4 mm deep hole with 1 mm dia drill bit. So at different points, so you are marking those different points as 1, 2, 3 or 4 or so. So that way you will be drilling. So basically you are advancing initially 50 mm so as to establish the quasi stationary state of welding, and then you are drilling at these points. You are drilling at all these points you are drilling holes. Now so, and in this you are embedding the hot junction of alumyl chromyl thermocouple in these holes, and and then these are filled with this high temperature brazing material using oxyacetylene welding. Now the other end of this thermocouple, so thermocouple which is there, so other end will be basically attached to the temperature recorder, so that when you are doing the welding, in that case basically you are able to record the temperature histories. So basically your purpose is to record temperature history or thermal histories of these points. So that will be during welding. Now once so when you are proceeding, so you will have all these points, and these points as its other end will be connected to the recorder. Now all these points will have different temperatures, because the temperature, maximum temperature will be at the center, where in certain direction. So in this direction, suppose the welding is proceeding, and then you will have the different temperatures at these points. So these points will be recorded. Now you will draw the the thermal history of the point along the transverse section. So you will have this this is the transverse section. So along the transverse section, which is where you have taken the different points, you will draw the thermal history. Now the thermal history basically will be looking in a certain pattern. Now if you look at the first point, so basically it comes like this. So, this will be basically the first point. So, this will be for the first point, and similarly if you go for the second point. So, it is going like this, third point will be going like this. So, that way you will have the fourth point goes like this. So, this is the thermal history which is basically drawn after you get these temperature through the temperature recorder. Once you get these values, then in this axis you will have time, and on this axis you will have temperature. So, as the time basically is proceeding, so with time there will be initially you will see that the temperature has increased, and then finally it is decreasing. So, this kind of pattern will be shown, and this will be the points 1, 2, 3, 4. So, that way for the first point it will be maximum, and then you will have the second point, the third point, and the fourth point. So, accordingly the temperature basically will be decreasing. Now, from these histories you can have the you can find so you will be having the different depending upon the different cooling rate. Basically you will have the cooling rate determination in different directions. So, what if you look at the same geometry in this case? Now, what you see that you will be looking at, so you will have this as T1 temperature, then you will have the T2 temperature, T3 temperature, like that. Now, accordingly you will have you can find. So, what you see you can draw these thermal histories. So, now if you look at the different points, so you will have the one point here, then you will have second point here, you will have third point here, then you will have fourth point here. So, if you try to see so if you, after a certain distance we are trying to have these thermal history. So, what we see that we are getting initially you have such kind of history, then further you will have the history will go like this, then you will have so such kind of things will be repeated. So, such way. Now, the thing is that you can have the determination of the cooling rate in different directions, like maybe if this is the direction for the K, and then you have L, then you have M and N. So, basically you can have the cooling rate determination in the different directions you can have and based on the cooling rate basically you can further predict. So, that also we will study that once you know the cooling rate, then this cooling rate basically can be utilized for predicting the effect of this heat flow, because ultimately it is going to a higher temperature, and then further there is decrease in the temperature. It is like a kind of heat treatment process. So, accordingly you can have the effect of these heat flow on the structure of the material. So, it was so basically one of the researcher has shown that if you typically see the shape of thermal histories for the different type of processes, what was seen that in the case of the electroslag welding, this it was showing coming like this. So, if it is a T max, if this is the maximum temperature in this case, and so in that case this will be your T max, and this way it goes for the electroslag welding. Then behind that there was the submerged arc welding. So, this was submerged arc welding. And if you look at the manual metal arc welding, it is further steeper. So, that will be your manual metal arc welding. So, basically in the case of manual metal arc welding, it goes even in a steeper manner. So, the heating also is somewhat changed in the case of these different welding processes. And also it also depends that depending upon the material also you will have the different level of cooling rate being established. It will be depending upon the what will be the size of the weld, or what is the thickness of the parent material, because as we have understood, we have seen the effect of the different parameters. So, there we have seen that as the thickness will be changing. So, since it is working as a heat sink, so there will be different effect on the on its ability to take the heat away from it. So, accordingly you will have its effect on the properties of the material. Cooling rate will be changed. When you have a thicker material, you will have a different cooling rate, you have a higher cooling rate, and that cooling rate basically that we can further superimpose on the TTT curve that we will see, and then we can predict what will be the transformation products in the case of welding. So, the important points which we need to know also in such cases, that we need to know about the critical cooling rate, because once we know the thermal history, once we know the cooling rate, then we basically depending upon the critical cooling rate, as we know that if the cooling rate is established, and based on the value of the critical cooling rate, we can further say that how that transformation will proceed, because as we know that critical cooling rate is the rate that is minimum cooling rate which is required for transformation of the product, that is martensite. So, you can have a prediction of the formation of these products which are like martensite in the case of the the sudden quenching. So, what we have seen earlier. So, here also once you establish the cooling rate by finding the thermal histories, then if that is more than the critical cooling rate, then you can say that you will have a martensitic structure formed. And typically many a times, as we see if you have a specimen in such a manner that it is surrounded with the metal, or you have higher cooling rate, even in the case of air cooling also, you will have the chance of, and if you see that the cooling rate which you have achieved, it is going beyond the critical cooling rate, you can ensure of having martensitic structure. If the cooling rate is not beyond that, in that case you will have to further use the TTT diagrams. So, as you see that so in the case of martensite formation, that can be understood using that critical cooling rate. Otherwise, if the cooling rate is not up to that standard, so that cooling rate can be seen by looking at the TTT curves, and as we see that your TTT curve goes like this. So, you will have the transformation start and then transformation finish. So that we have seen. So what happens that if your if the cooling rate is such that it is beyond the it's more steep. So if your cooling rate is steep, then you can have, so below that you will have the MS and MF. But if it goes in between the transformation line, so you will have the different percentages of transformation. So if the cooling rate will be less than this critical cooling rate, then certainly there will be pearlitic transformation from austenite. So austenite will be transformed to pearlite, and based on where it ends, you will have the coarse pearlite formation, or you have the fine pearlite formation, and also accordingly you can predict that there will be either benetic transformation, or otherwise we have studied about other type of transformations, like the formation of benite will be there if it is past the nose of the C curve and then you are holding here. So now that again also depends that how you are basically managing this TTT curve, because in the case of normal materials, when your nose will be here, suppose you will have the chance of some cooling rate that will produce martensite. Now when your when you have lower hardenability, so in this case even with the higher cooling rate also, there is very less chance that you are going into the martensitic zone. So basically you will have some pearlitic transformation. So what we do is in such materials we are try to increase the hardenability by the use of alloying elements. So these alloying elements basically will be shifting the these TTT curves towards the right. So many a times we use the alloying elements in the filler material. So its job will be, because you have the transformation in a particular zone. Now that undergoes the transformation. Now in that zone it depends upon, because anyway the material which has already the alloying elements. So with those alloying elements, certainly the hardenability will be changed. So if you can have the alloying elements by so if you are adding the alloying elements in the weld pool, so it's when it is getting solidified, then after that temperature, say when it goes to the in the transformation temperature range, in that case for those materials the TTT curve will be behaving differently. So once you increase the so in those cases your this line, this move like this. So many a times you have even with this cooling rate also you will be able to get martensite structure, whereas in this case you are this is just touching the nose. So basically the nose is shifting because of these alloying elements, and that tends to increase the hardenability of the material, and the critical cooling rate that value will be even lesser, and even at lesser cooling rate you will be able to achieve the martensitic structures. Now these the material which undergoes this thermal treatment, that can be nowadays even studied, or that can be seen using typical weld thermal simulator. So nowadays there are standard equipments which are available, and there basically you can simulate, you can have the study of that how these different during the welding, how the temperature is varying, what way the thermal histories are getting generated. So for that there are weld thermal simulator, and basically the thermal cycle which is experienced by the specimen that can be duplicated using these machines, and you have a standard apparatus for that, and it is known as the the Gleeble. So this is Gleeble. It is a registered trademark of the dynamic system. So that way it is the registered trademark. So in that basically for the dynamic system. So in this what they do is that they keep the, so you have the jaw, so in that they fix the jaw, then they are heating the specimen using the resistance heating method by passing the electric current through the specimen, and you have the jaw which is water cooled and it is holding that. And then you have also the thermocouple which will be spot welded to the middle of the specimen, and then you have accordingly you can have the experience of the thermal history, the simulation, how the specific thermal cycle is duplicated. So basically there are many applications of these Weld thermal simulator. So what it can do is it can basically be used in conjunction with high speed dilatometer so to help construct the continuous cooling transformation diagrams. So basically using that Weld thermal simulator you can use you can have the high speed dilatometer, and then you can find the continuous cooling transformation diagram, which will be further be able to predict the kind of microstructure as we have already seen that how the continuous cooling transformation curves can be used to predict the microstructure. Then you can have the high speed tensile test during the welding. So high speed tensile testing during the Weld thermal simulation. So that will be telling us that what will be the property of the material at elevated temperatures. If you do that, what will be so if you do the testing also, so that will be able to tell us that what will be its elevated temperature ductility. So it will to find elevated temperature ductility and strength of metal. Okay. Then we can also prepare the the Charpy impact test specimens, and we can further subject these specimen to various thermal cycles, and that way these results can be used for the industrial applications. So basically many times these instrument which is popularly known as the Gleeble, that is basically they are developed by Nippes and Savage in 1949. So originally that was the original device that was developed, and then this dynamic system, trademark of dynamic system, this instrument is, and this is a very, so you can have the feel about the thermal histories, then how when you have the welding going on. So, for that welded specimen or so, how its property will be changing. So, this way you can have one understanding about the change in the properties of the materials. So, that is about the weld thermal simulator. However, it has also certain limitations. So, because you have a very extreme extremely high cooling rates are there during the certain type of welding processes. So, which you cannot reproduce in these processes, because you have the limited cooling possible. So, that is there. Then also the limitations are there regarding the heat losses from the surfaces. So, certainly there will be issues related to that, but still you can certainly have a feeling about the process, you can have the feeling about the thermal histories, and proper understanding can be developed. Thank you very much.